Hello everybody and welcome back to another Brave video. Today I'll be going through a very common question type that I'm sure many of you have seen. It's a question where we have a cell in solution and then we change the solution and we're seeing the corresponding changes to the cell's volume. And based on this, we are supposed to determine the osmolarity of the surrounding solution and how it has changed. Now, this is a variation of that question, however, it's slightly more challenging because it requires you to think about something that many of you have never thought about before. It's a concept that I'm sure you're aware of, but you never actually applied it in this situation. And because of that, I'm going to let you guys solve the question first by yourself. So please pause the video, try your best to solve it, and if you can't, we'll go through the solution in a second. Okay, so hopefully you had a go. So let's go into it. So the cell in the diagram was in an original solution that is approximately isotonic, i.e. equivalent to 150 millimolars NaCl. The solution was changed, and which new solution would best account for the change in the cell's volume shown in the diagram. So what can we see from the diagram? So this is the new cell, the changed cell, and we can see that it's definitely increased in volume. It looks more swollen, and this means that water has entered the cell. Now, water entering the cell means only one thing, and that means the surrounding solution is hypotonic to the intercellular concentration in the cell. So hypotonic means a lower concentration of solute in the outside solution. That means that from our original, which is here, which is 150 millimolar, right? Which it says here, 150 millimolar NaCl, we're going to a lower concentration. So that means that we're looking for a composition in these options that has a lower concentration than 150 millimolar. Now this question is challenging because if you look at the options, we have quite a few that's lower than 150 millimolar NaCl. In fact, all of them are. But we also have this factor of CaCl2. We also have this factor of glucose. Now, how do we incorporate that? Now, if you got stuck here, don't worry. This is where most students get stuck. And this is because you're not thinking about the big picture here. And I will quickly show you what I mean by that. So we have 150 millimolar NaCl, right? Now, this would be the only contribution to the osmolarity of the solution if NaCl wasn't an ionic compound. If you're aware, you know ionic compounds are going to dissociate in solution. And when it dissociates, we're going to get Na plus ions, we're going to get Cl minus ions, right? But how many are we going to get? Well, actually, we're going to get the actual concentration but of each ion. That means we'll have 150 from Na plus and 150 from Cl minus, right? Now, what does this contribute, right? Now, the concentration of NaCl is the same, right? We'll keep this as millimolar, but we have a new concentration here, which is 300 osmoles. Osmoles is the concentration we have to think about here, the concentration in osmoles, because we're dealing with an ionic compound, meaning that the actual contribution of concentration is not only 150 millimolar, it's actually 300 osmoles due to our 150 from each constituent ion. Now, when we think of that, this becomes a whole lot easier, because immediately we can look at this one and we can say 50 millimolar NaCl, that's going to be 100 osmoles, right? We're just timesing it by 2 because it's NaCl. And then 200 millimolar glucose. Well, glucose is not going to dissociate the constituent parts. It's just glucose. That means we can add that to our 200 osmoles of glucose. And that's going to give us 300. And 300 is the same as our original, right? We determined that our original 150 millimolar is 300 osmoles. So what does that mean? These two are isotonic, right? This is isotonic, right? We're looking for hypotonic. So it means instantly we can discard this. Let's look at B. So in B, we have CaCl2, which is interesting, right? So let's write CaCl2 here, right? How would it be different to NaCl? Well, as you see here, we took apart the constituent ions. So let's do the same thing for CaCl2. We have Ca2 plus, and we have Cl minus. But if you look here, we have 2 Cl minus. So that means we have 3 constituent ions. Now, 3 constituent ions means that instead of timesing our concentration in millimolar by 2, we're timesing it by 3. So here, we're timesing 50 millimolar CaCl2. That's going to be 150 osmoles, and we're adding that to 200 osmoles of glucose, right? So 150 plus 200, that's 350, okay? That is what we call hypertonic, right? Now, if it were this solution, we would see a shriveled up cell. It would not be swollen like it is here. So that's also wrong. What about C? So C is a pretty simple one. We're just timesing our concentration by 2 because it's NaCl. So we have 200 plus 100 in glucose, and that's 300, so we know that's going to be isotonic. Okay, what about D? Well, we have an ACl again, so we're timesing by 2. Timesing by 2 for our value gives us 66.6, and we're adding that to 200. Now hold on, that gives us 266.6, and that is less than 300. So what does that mean? Well, that means this solution is actually hypotonic. Exactly what we're looking for, right? So we're pretty confident in D here. We'll just go through E just to make sure. So E has CaCl2, meaning we have to times it by 3. 33.3 times 3 is 100. 100 plus 200 of glucose is 300, meaning this one is also isotonic. That means that our only possible option is the one where it is hypotonic, which is D. And that's why D is our correct answer. So if you got the solution by yourself, great job, because this is something many students don't actually think about. But remember, you have to think about the big picture when it comes to ions in solution. It's not just 150 millimolar, we're talking about 300 milliosmoles. Okay, hope you enjoyed the video. See you guys in the next one.